junction exclusively there. There are some acetylcholine receptors in the brain, but very few. Okay. Most of the other ones, you can basically divide them up into several different types. The plain old amino acids, you'd be surprised that glutamate and aspartate, lysine, these are part of the 20 essential amino acids, okay, that we learned about that we need to make proteins. So your brain is using these as transmitters as well. Okay. The acetylcholine monoamines here. I'll show you how these are derived in just a second here. And then the purines, adenosine, ATP, GTP, the guanine triphosphate, some of their derivatives, they can also be used as neurotransmitters in the bone. And in addition, you've got some peptides, some short amino acid chains, okay, like oxytocin is a common one you might read about. That's supposed to be very important for bonding and trust. And it's been shown that, like mothers who have very low levels of oxytocin don't bond with their newborns very well. And you can actually, they can do psychological studies where people play games and trading and where you have to trust each other to do things. If you give them a shot of oxytocin, the trust levels go way up. And it's really interesting how that works. And they're finding these all the time, so I certainly don't expect you to memorize any of these things. But the main ones in the brain are going to be the glutamate and GABA, so they're amino acids. And I've got on the next slide, we'll talk about them a little bit here. I just wanted to briefly mention nitric oxide. This is it's produced in the cells, and it affects especially smooth muscle as well as some of the neurons as a neurotransmitter. You've probably heard about people taking their nitroglycerin for chest pain, or they call it, my father-in-law called it his dynamite pill. What that does is basically it's broken down and releases nitric oxide. That causes the smooth muscle in the arterioles to relax. It opens them up, and then you get greater blood flow through the heart. But it's doing that in the rest of the body as well. So that's why sometimes the blood pressure will drop and people will pass out. They were actually trying to work on that theory or that aspect and find new drugs for blood pressure management that use nitric oxide to lower the blood pressure. Okay, and they did that to a big group of people, and a lot of the guys for this one particular drug had the interesting side effect that they were getting very easy erections because they were dilating the smooth muscle in the penis and getting erections. That's how Viagra was discovered. They were looking for a blood pressure agent, and the interesting side effects of the people in the trial made them switch, and now they've sold millions of dollars worth of Viagra, and it's not used for blood pressure. But that's why they tell you not to use it if you're taking nitroglycerin, because the combination can cause you to pass out, low blood pressure.
Low blood pressure.
So anyway,
I
okay.
got one question. Why do they put that in pre-workout for like to go to the gym and stuff? They got it's not it's not just nitric oxide by itself, but it's NO3 is what it's in stuff I'm taking now.
NO3 is nitrate. That's a little different. That's not nitrous oxide. Nitrous oxide is NO.
But they had some of that stuff in it. Like some of the pre-workouts that I have had just nitric oxide in it.
That's a gas.
Well, somehow it makes it, because it says it opens our veins up when you take it.
Maybe it's something that's broken down into nitrous oxide.
And then making you.
Yeah. But theoretically, if that's what it is, that's what it would do. Yeah, it will dilate those vasculature. Okay. But nitrous oxide itself is a gas. Okay. It'll just diffuse right through the cells. It doesn't even need to be held in vesicles and released. It just, once it's made, it will diffuse out. And this is just, again, to state that glutamate is the major transmitter in the brain. Over 90% of the synapses are some other major, even though, like I say, almost all your receptors are these two, you have some important other transmitters like serotonin and dopamine. The dopamine system is part of the limbic system and part of your pleasure centers, your addiction centers, and things like that, where you get pleasure from. So that's why you're trying to stimulate the dopamine system when you take cocaine and amphetamine and these sort of things. That's what you're going after, is to affect those dopamine receptors. And okay, that's enough on that. I just want to show you biogenic amines. This sounds like an easy one to ask a question about. And basically, these are amines that have been made by the neurons into neurotransmitters or into other products that they're going to use. Usually starting with an amino acid, like histidine is made into histamine, and I'll show you how that works in a second. But so biogenic amines, these are secondary compounds that are made by your system. You don't really find these out in the world very often. Okay? They're not necessarily in the diet, except for something like tyramine, which is a breakdown product, and especially in aged pickled foods, bologna and dill pickles and cheeses and things like that. Some of the bacteria that's active in causing some of that aging, especially in cheeses, will break down the amino acid into tyramine, and then that is vasoactive. That will cause headaches and things like that because it causes the blood vessels to dilate or constrict. Okay? So a lot of foods, I had several patients that would get migraines if they ate dill pickles. Okay?
Oh, I was
A lot of
was the salt. I just, for some reason, just assumed it was the high salt because you're pickling it, and I thought it was just increased salt in the pickling. But interesting.
Not that I know of.
Okay.
I haven't really actually heard of anybody getting headaches from high salt content foods.
Okay.
But otherwise, you get headaches from, well, you can get headaches from salted pork and stuff like that. But it's mainly the tyramine, because that's aged.
Okay.
So, um,
Interesting. Yeah, right?
okay, and and then some of the catecholamines. These are broken down into amines from amino acids as well. And this is where we get epinephrine and dopamine, and I'm going to show you that pathway here. So just have a basic idea of what a biogenic amine is. It's these active compounds that they're amines, and I'll show you why here in a second. Here's the amino acid histidine. Okay, here's the acid. Here's the amine. And this is the side chain. Okay, this is one of the 20 that we need to make our proteins. So what the body does, there are all sorts of enzymes in the body called carboxylases, and it'll hack off that and form carbon dioxide out of that. Carbon dioxide and water, basically. Okay, and now you're left with just an amine hanging on the end there. Okay, so this is what we mean by the biogenic amine. And we all know what histamine can do. It causes welts and allergic responses and that sort of thing. But it's also a neurotransmitter in the brain. Okay? And that's why when you take an antihistamine, you get sleepy.
Yeah.
Okay, that's the neurological side effects of taking an antihistamine, because you're blocking the histamine receptors in the brain. Okay? And it's responsible for alertness and that sort of thing. Okay.
What happens if it makes you hyper?
I'm sorry?
Like if you take something like Benadryl or something and it makes you hyper,
Well, not
instead of
normally.
making
I mean, you can have people that get paradoxical side effects, but most people get sedated from it, get sleepy from it. That's where they put Somanex as a sleeping medicine, is Benadryl. Yeah, it's just, you can buy Benadryl cheap, but don't worry about buying Somanex. You
Yeah.
get the generic Benadryl and the Somanex. In fact, yesterday I got really kind of goofy and sleepy because I took one for some congestion and just barely able to get through the work. But you'll notice diphenhydramine, this is an antihistamine. Okay? It blocks the effect of histamine, and it's not only going to block the allergic effects, but it's going to block the neurological activity as well and make you sleepy. But they found, this is the interesting part, in the 1960s it was found that the same drug, Benadryl, diphenhydramine, inhibits the reuptake of serotonin, which is exactly what you want to do in depression. Okay? start. This is Benadryl right here. This is its structure. Now you can see they probably went through hundreds and hundreds of structures building similar molecules but just varying little points on them. And they came up with this one here. This is definitely an artificial molecule. It's not natural with these 3-fluoride compounds on it. That's Prozac, but it's got the same basic structure as Benadryl. And that's why. Because they were trying to mimic the effect of Benadryl without putting people to sleep, without making them drowsy.
So you said it inhibits the reuptake?
The reuptake of serotonin. In other words, serotonin is the neurotransmitter in the vesicle. It's dumped in the synapse, and it does its job on the next neuron, but then it's pumped back in to the neuron so that it can be put back into the vesicle.
It doesn't let it pump it back in.
And it blocks that reuptake is what it does. So it keeps the serotonin in the synapse longer, and you get the effects that you want, mainly an antidepressant. Okay? And so that's why they call them selective serotonin reuptake inhibitors, SSRI. And you can see Zoloft is another big one which has a very similar structure with 2 benzene rings, a couple of carbons, no amine. So and I'm sure they made hundreds of these things and tested them all. These just happen to be the ones that work the best. So that's what chemists do in pharmacology labs. Is just randomly stick things on here and then test them and see what happens. So, but at least they had a guide drug to go by because they were trying to sort of mimic this basic shape. Okay? So you can see that these things fit in the same receptors.
And on the Benadryl, what is the active ingredient that causes sleepiness? Like it's just the way that chemical is made, so when they change the
Well, you couldn't predict it from just looking at the shape.
Mm-hmm.
I mean, it was just found, okay, that Benadryl acts as an antihistamine. Okay, so it's blocking those receptor sites.
Mm-hmm.
Okay, but it also blocks the reuptake of serotonin.
Mm-hmm.
So they're trying to develop these so you get the antidepressive effect, but you don't get the
So
effect.
what she's saying is,
You can't
what
take
in
Prozac
that,
for allergies, in other words.
but when
Right.
you're looking at that, what part of it can you say
Is the sleepy part?
keeps you
Is
from
the
going to sleep and the part
nitrogen?
that,
You can't.
You don't know.
You couldn't predict that.
Okay.
You couldn't predict that. I mean, it's because you've got an ether linkage here between 2 benzene groups, and it has to be that just because a little change in the shape, you're affecting the receptor a little bit differently, and that's all you can say. Okay? I'm sure now they actually know exactly where it fits, okay?
Right.
Because now they do it more scientifically. They'll actually measure the dimensions of a receptor site on a protein, and they'll design a compound that fits in there without even knowing what's going to happen. Okay, so they'll try to block receptors. So the chemists are getting real sophisticated now. They don't try it necessarily hundreds and hundreds.
so what
of
they did
things.
was basically they took that and started changing it a little bit and then tried it on somebody?
Yeah. Well, they have assays that they can do. They can see, they can get neurons to see if it blocks the reuptake. They don't have to do it in a live body. So that's why they can test it that way.
And the reason prescriptions are so expensive, is it because of all the research and the handling and everything like that?
Takes, you've got thousands of chemists running millions of different tests on different, hundreds of thousands of compounds and
Right.
assays. It takes hundreds of millions of dollars to get one drug to market. And so they try to get their money back while they've got the patent.
Right.
I think it's 7 years. They've got 7 years to make their money back. So then it goes generic.
Right.
And anybody can make it. Okay. Here's a few things that you might find interesting. Here's the tyrosine. Okay. This is a normal amino acid. This is one of the 20 that we use to make protein. Your body uses that one. The neurons use this to, they'll put a hydroxyl group on the benzene ring here. That's the next step. Okay. Then they decarboxylate it just like the histamine. Okay. Now you've got an amine there. This is dopamine. Okay. This is the compound that affects your mood and that sort of thing. It stabilizes your mood, elevates the mood. Anytime even when you're expecting something good to happen, your dopamine levels rise. Okay. So anticipation is sometimes more fun than the actual event. But look how, without the hydroxyl groups, look how similar that is to these other things here, methamphetamine.
Yeah.
Okay. You've got the benzene ring, a couple carbons, and then a nitrogen. You've got benzene, a couple carbons, and a nitrogen. You just vary it a little bit, and molecules very similar in shape. This is what everybody's after with, you take phenylephrine and pseudoephedrine and ephedrine. All you're doing is knocking off this hydroxyl group right here, and you've got meth. That's what the meth labs are doing. And you can get this, and sometimes it's hard to get a lot of it nowadays because they're starting to watch it. They're keeping it behind the counter now.
Show your ID.
Yeah, but it's still not prescription.
So why is it when they fire that up with a lighter or whatnot, it doesn't change the molecule? I thought, I mean, why doesn't the heat change it?
Well, you're basically just vaporizing it, just like boiling water. You're not really changing the structure.
Stay the same.
And it's a fairly simple, stable molecule too. I mean, it would be hard to. You'd have to burn this, actually burn it to get a real change. But you just heat it up enough so it vaporizes, and you can snort it that way. So, but look at even how similar that is. Methamphetamine is to ecstasy. What they've got, the two hydroxyl groups over here, but they connected them with a carbon so that they're no longer alcohols. These are ethers now, and there would be much less hydrogen bonding, so it's more likely to get through the blood-brain barrier this way. Okay. So, and Ritalin, okay, benzene group, two carbons and amine. Okay. Some chemist, just like they did with Prozac, some chemist was looking at these things like this, and he was saying, how can I change it a little bit? All he did was complete the ring here with two more carbons, okay, and then put a little side group on here, and said, let's try it. Okay. So these things don't come out just by chance. Well, sometimes they do by chance, but chemists are making hundreds of molecules, varying little things in different little places just to see what they do, see if they're neuroactive.
I have
Yeah.
a question.
Yeah.
Whoever. So, well, how does one cause certain effects and then that, like this one causes hyperactivity, I guess you could just
Well, they all
simply
do,
put it.
basically.
The Ritalin,
Ritalin?
I thought the Ritalin.
It's a paradoxical effect in kids.
Right.
Oh, okay.
Adults it's seizure.
It actually calms it down. Okay, but you can give Ritalin to adults, and they can
And it's
fire
the
them up.
same as the.
Okay.
Ah.
And but this has to fit into a receptor, basically, right? Okay, so you can make a molecule that mimics it and actually is an agonist for the same effect of something like dopamine or something like this. But you can also make molecules like this that could block those receptors because they're so similar in shape. They fit in the same receptor, but they don't activate them, they block it. Okay? So, and you can't always predict what is what. Okay? I just thought you'd be interested to see how close these things are related. Because this is epinephrine, this is adrenaline here. All you did was put that hydroxyl group on there, okay, and then you put a methyl group on the amine right there. Okay. So epinephrine, look how similar in that is to ephedrine. Okay. And that is why ephedrine makes you jittery. Okay. That's a decongestant. It's a sympathetic stimulant. Okay. The sympathetic system, it's adrenergic, it looks like adrenaline. Okay. So when you give this in the fight or flight, you don't want to be having runny noses and losing all those fluids. Okay. So if you give a sympathetic stimulant like that, you're going to dry up the sinuses. Okay. That's the whole reason that ephedrine is used. Okay. Because it's a sympathetic stimulant.
Unlike the drugs, what is it in it that makes you so, like ecstasy, it makes you, like your body tingle?
Well, it's getting into other receptors too. I mean, it's not just the same receptors for adrenaline and things like that, but you just really can't predict. Like one little change in that molecule might even work better than ecstasy. So you can't really say exactly what's doing the effect, because it's got to fit in those receptors. Okay? And some of them are going to be a little different. They may not fit in all the receptors that adrenaline fits into. Okay? This is a little different amino acid here. This is tryptophan. This is the one people say is supposed to make them sleepy after a big turkey dinner.
Turkey.
Okay. There's actually more tryptophan in pork, so
serotonin do?
It's mainly in your mood centers, and lack of serotonin, low serotonin levels will cause depression. So you want it elevated to take that. But look at how you've got the 6, 5, and then over here you've got 2 carbons and an amine. Okay, 6, 5, 2 carbons and an amine. So you can almost see how this structure right here will fit in the same key, in the same hole as serotonin. That's why LSD is neurologically active. Okay, and it's actually fitting in those holes in weird ways. Okay, and it's the natural acid, lysergic acid. This is an acid, not an amine. It's got an OH group here instead of this. This is the artificial part that we put on. Okay, that's where the D comes from, the diethylamide. Okay, but lysergic acid is naturally derived from fungus that grows on rye and some barley and plants a little bit. It's a natural hallucinogen, and this has been discovered many times that, you know, if you take rye, especially that's been a little damp, okay, and it starts to get the fungus, they call it a rust, or like a black stuff on it. If you make bread out of that, or you know, bagels or whatever, everybody that walks into the bakery that day is going to be hallucinating on the way home. And they think, I mean, this actually happens in Europe. The last time, a few years ago, I read an article about half the town was walking around having a LSD trip.
They have to eat it,
But but they think this is also the cause of the Salem witch trials. They think all the hysterics that were going on and visions and hallucinations was due to this because they ate a lot of rye. And they looked at the weather right at where the trials were happening, and for 2 years it had really wet summers, and the rye was going bad, and people were writing about how the rye was bad.
Oh, so the actual rye, the
The
plant
Yeah,
that they made it out of?
yeah.
Oh,
Yeah, the fungus is on the plant.
the actual
So when they make
plant.
bread out of it, it's a contaminant in the bread.
So you didn't have to
Oh.
eat it, you didn't have to eat it, just inhale the.
Well, no, you ate it.
Oh, okay.
Yeah, they ate the bread, so that's what caused the problem. But it's just interesting how these structural things are related, and that's the kind of point I'm trying to make. That most things that are neuroactive are acting like some sort of natural brain transmitter.
Right.
And I'm glad you guys don't freak out when you see structures like this anymore. You kind of understand what's going on, don't you? See the carbons.
What's LSD?
Maybe we'll do an extra credit question, and you have to give me the molecular weight of this. Okay. Remember,
Say it one more
how
time.
do you add your hydrogens now? Okay. Remember, there's going to be 2 there. There's going to be 1 there. 4 bonds to every carbon, right? Okay.
What's LSD stand for?
Lysergic acid diamide, diethylamide.
Is that why shrooms can also make you hallucinate because it's fungus?
That's mescaline, and I don't know the structure of mescaline, but I think it's more related to some of the others, not necessarily this one. I could look it up real quick though.
Well, because those shrooms do you think it comes from like because it's like from the cow and the manure, so like the cows and the rye and stuff.
Oh, yeah.
That could be part of the reason.
Well, no, they're eating the mushrooms, the special mushrooms that grow in manure,
Yeah.
and mushrooms are fungus, just like the rust, just like this fungus. Okay, so they're producing something pretty similar, but it's definitely neuroactive too. That was big back when I was in
Yeah.
college. Everybody
You when you do
Well,
with
They still do.
you get
still do.
like I after brain.
This question, and I'm just kind of
right there.
trying to figure out how they go about deriving all these different things. You said they tested against neurons. Where are they getting these neurons from? Are they getting them from donors or?
Probably rats.
Okay, so,
Yeah, they can just see if it blocks the receptors, because remember, they're mammals.
yeah,
Oh,
They're
okay.
going to be very similar receptors, just like us.
Okay, I was just kind of trying to figure that out in my head. Okay.
This is Valium. This is really an artificial compound here. There's these kind of 7-member rings. These don't occur in nature. okay? And I'd have to actually look it up to see what the prodrug was that they were trying to copy when they came up with this diazepam structure. So I'll try to find that one day and put another slide on it. But you see what it does. We talked about the GABA receptors being inhibitory, right? Okay. So this activates the GABA receptors. It lets the chloride channels dump in chloride, so those neurons become less likely to fire. And so if your problem is anxiety, you're sort of overfiring in those areas, right? You just calm them down. All you're doing is bringing that negative level down a little lower. Okay, so that's what Valium does. Same as Xanax, Lubrax, they all have similar structures. Okay, so okay, I think that was the only point. We've already done this, so let's start the eye here before we run out of time.
And there's really no difference in like a generic and a name brand, really?
Well, you can't say always, but usually if it's a good company making the drug, it's pretty similar, yeah. But, you know, if they're getting some cheap knockoff from China and their production facilities not doing the job of purification, you can't always be sure, but most of the time they're pretty good. Come on. That's the ear. All right. There's the eye. That's real though. That's not Photoshop.
Oh my God.
Yeah.
You can do that?
Yeah.
Oh my gosh.
There's lots of people that can close their eyes out. There's people that can do it on call. They don't even have to pull their eyes out. They just go and
Right.
their
Wait,
eyes
I've seen
Yeah,
those
really
people
people
do
pop
that.
out.
That's disgusting.
That's disgusting.
I've never seen that. That's like I do.
But all right, this is what we might call a normal eye.
Where is the eye? At the end.
Everybody knows what the black spot's called, right?
Pupil.
The pupil. Okay. So why do people miss it on the final?
Well, now.
They forget.
Somebody always leaves that blank for some reason.
Color signs.
It's the opening in the eye. It's basically a space, it's just the opening in the eye, iris here, okay? These fibers go from this outer circular part here to there, so that's a dark space where the light's going through. That's the pupil. This is the iris, where you get the different colors. And you'll see that sometimes you get sort of grayish looking, bluish, yellowish, brownish eyes. It depends on what size these fibers are and how much melanin is in the iris. Okay, that's how you get eye color, and I'll show you a little bit better here on the next slide. But remember, your lacrimal gland is on the upper outer side. Okay, so your tears are going to flow over your eye and then down through the lacrimal duct here in the corners.
So it doesn't actually come from there.
I'm in here.
From in here?
Yeah.
No, it comes up from underneath your eye up top. It just flows underneath the eyelid. Then the white part of the eye, okay, the lining is called the sclera, but the actual surface is called the conjunctiva. Okay, so when you get conjunctivitis or pink eye, all the blood vessels in this conjunctiva here get dilated and red and that sort of thing. I'll show you a couple pictures here in a minute. But don't worry about right now, because I'm going to show you the whole eyeball and we're going to go through the whole structure. Okay. Real quickly though, this is how you get eye color. If you've got real dark eyes, dark brown or almost black eyes, the iris, you've got heavy melanin in both layers of the iris. Okay, this is where the light would be coming through. This is the end of the iris here. Okay, so this would be the hole here where the light comes through. So this is going to give you real dark eyes. The lighter this gets with melanin, the more brownish the eyes are going to look. Okay, if there's not much melanin in that first layer at all, light will come through, be absorbed and reflected out, and depending on the size of the fibers running in the iris, you'll get different colors. The gray eyes kind of come from larger fibers in the iris. If they're real tiny fibers, like little collagen fibers and things like that, they will absorb light and reflect the blue. Okay? So there's nothing about your eyes that are actually blue. It's the light that's with blue that's reflecting off of them. Okay? And that's why eyes don't look so blue as you get into a darker room. Okay? That's why blue eyes look bluer if you're wearing a blue shirt. Okay? Because the light's reflecting off your eye.
Yeah.
Okay? But now, if you have a little bit of both, you've got the small fibers and a little bit of melanin in that first layer, okay? You mix the yellowish color
one more time about the fibers?
See the size of the fibers here?
Mhm.
Okay. That your eyes are blue if they're blue. They're blue for the same reason that the sky is blue. Okay. The other light goes through. Okay. But blue is scattered by tiny, tiny dust particles in the atmosphere, and that's why it scatters blue everywhere. Right? So if you're looking at the sun, all the yellow and red light is coming right at you. It goes right through the atmosphere, and you see the sun as yellowish. Okay. But all the blue light is getting scattered on the way out this way, and then it's reflected off of things, and that's why the whole sky looks blue, okay, when the sun's high. What happens when the sun gets down really low is all the blue light is being scattered off to the sides, and you're seeing all the yellow and red light reflecting off the clouds and everything now. That's why sunsets look reddish. Okay? So the blue light is gone by the time it gets to you. So, yeah.
I was watching the news a couple of months ago, and one of the doctors stated that in the next 2 to 3 years, people will be able to change their eye color. How would that? So how do
I
we?
have absolutely no idea. Unless they're talking like picking genes in kids or something and changing eye color or something like that. But I have no idea how you would do it artificially. Like unless you're going to inject the iris with dye or something.
They're artificially touching their eyes.
I've seen
I
that.
saw that.
Tattoo
Yeah.
their eyes.
Ooh.
Right?
That's the
Now,
custom.
so, we're not necessarily born with all the melatonin that we're gonna have.
Right,
Can we,
right.
because my mom has pictures, baby pictures of me, and like the first, I think 3 months, I had blue eyes. And
A
now
lot of
obviously I have
almost all
brown eyes.
babies do
Start off with blue eyes.
start off with blue eyes. I mean that's Caucasians and blacks and Hispanics. And everybody doesn't have enough melanin in the iris, so the kids look like blue eyes, and it scared a lot of fathers when I was delivering babies.
Babies too?
Yeah, we live 200.
Well, that ain't mine. Did not.
Oh. So yeah, sometimes Dad is like, whoa.
Yeah.
What is it
I
like
know
when you have
it.
two color eyes?
It doesn't take too long before the color comes back.
What about,
Real quickly, this is just some of the variety of eyes that you might see out in nature. You can have a single cell that's sensitive to light, and the cell, I don't know if you have this, it's just, I'm not going to test you on it. But the better eye is when you start to form a cup, because then the eye can tell what direction the light's coming from. Okay, when bees are firing, this animal knows that the light came from that direction. Okay, so this is a better eye, even though it can't focus any kind of image. Okay, once you start to close off that cup, now you've got a pinhole camera. Okay, and you can get fairly good images on the back here now. Okay, if you've ever done that, take a cardboard box and just stick a pencil in it, just a little tiny hole, and then shine something like out here. The light coming through that pinhole will project the image on the back of the box. Okay, that's a pinhole camera. So, oh, there's a lot of speculation now that they use that to make the Shroud of Turin, the Jesus figure. They think that they used a pinhole camera and used light-sensitive stuff, and that's what projected the image. They just lit up a statue basically, and that's how they projected the image on there. And that's where the word camera comes from. Camera in Latin means room. Camera oscura means dark room with a pinhole. Okay, that's where the word camera came from. Anyway, so now we're putting lenses or fluid in here that help project an image here. Okay, and then even better is when we start getting transparent things like corneas and lenses here that can actually be stretched or relaxed to focus at the image better on the back of the eye. Okay, so real quickly, that's the story of the eye evolution. To make better eyes, you want more cells back here, more different types of rods and cones for seeing dark or for seeing colors or things like that. So, I want to go through this.
when you're light blind, you don't have as much of that?
You don't, your rods aren't working real well, because they're the ones that are most sensitive at night. Okay, your cones for color vision are right here. Your center vision is going to be coming down and focus an image right there where that little dip is. Okay? That's called the fovea centralis. Okay? And that's where most of your color vision rods are. So at night, actually it's better to look off to the side to see something, because if you look right at something at night, it's going to be much more blurry than if you look right off to the side and you'll see it better. Okay? Because your rods are out here, and this is where you get your night vision. Okay? So your peripheral vision is much more sensitive to light, so they're the ones that are firing at night, where your cone's shut down, which is why across the parking lot you can't tell if it's a purple car or dark red or brown or dark blue. It's really hard to tell the color because your cone's just on fire at night. So, and the best image, obviously, is focused right there, and you'd be surprised just how unfocused your eyes are when you get very far away from that. Okay, you can test that with yourself. Just take a book, look at one word in the middle of the page, and just stare at it and see how many words you can actually read above it or below it. You can't. You can't get more than a couple of lines, and then it's just too blurry to read. Okay, so you're really focusing right here. Once you get things out here, they don't focus very well. Okay. So the cornea, this is the clear part of your eye. Okay. And put that on your list. Or if you got this slide, circle that cornea, because that's going to be part of the naming game here. Because your final exam is going to look a lot like this. Okay. I'm going to put an eye, and I'm going to put 5 or 6 lines, and you're going to have to label things. So cornea, this should be on your list. The anterior chamber, this is the water-filled part of the eye in the front. Okay. That water-filled area is called the aqueous humor. It's not up here on the list. Okay. Aqueous, as in water, A-Q-U-E-O-U-S, aqueous. Okay. Humor, okay. H-U-M-O-U-R.
And that's where
And where is that?
That's in this anterior chamber.
Okay.
That's the fluid behind the cornea. Okay. And it flows underneath the iris here. Okay. Look up here. It flows underneath the iris and goes in. This is called the posterior chamber, right up in here. Okay. So that is fluid up here. The rest of the eye is filled with a gel-like substance. It's not water. Okay. And you'll see that when you cut open the deep eye. There's a little hole right here that drains that fluid and keeps the pressure from getting too high. This lets the fluid go into the venous system and flow away from the eye. When this is blocked and this is not working, that's what causes glaucoma. Glaucoma is an increased pressure in that fluid in the front of the eye. Okay.
Is there anything you can do to keep from getting that?
Not keep from getting it that I know of, but you can treat it. They'll go in with lasers and burn new holes,
Right.
and things like that.
No preventative.
Yeah.
Does smoking weed really help that?
So what?
Smoking weed really help glaucoma? You hear that all the time.
Well, they say. I haven't really seen the studies to tell you the truth.
What is that called?
Glaucoma.
No, the hole.
Oh, it's called the Canal of Schlemm, or Schlemm's Canal. Okay.
Schlim?
Schlemm. Probably Dr. Schlemm discovered it. Okay. Okay, that should be on your list too. And the iris should be on your list. The lens right here should be on your list. And you can see it has sort of a tree ring kind of structure here. That's embryologically, that's how it grows. It gets bigger and bigger by putting on more rings. Okay. During development, there's an artery that comes up through the middle of the optic nerve. Normally, they will spread out over the retina on the side, so that there's one that stretches all the way up and supplies the lens during the embryo development. Okay, and then that atrophies and disappears, and basically you'll never find this iris canal when you look in the eye. It's gone. Okay. So the lens, you'll notice, is attached. Just call these suspensory ligaments is the easiest way to remember that. It suspends the lens. Okay. And they are in a normal state of slight tension, pulling on the lens, and they are attached to this, what's called a ciliary body right here. Okay. And that is a muscle, a smooth muscle. Okay. So you can imagine what happens. I've got a certain amount of tension on the lens. Okay. When I stimulate that smooth muscle, it's a donut shape. So when they constrict, the donut's going to get smaller, right? So it's actually going to relieve the tension on the lens, and and the lens, which is being pulled out a little bit, relaxes and it widens, and that is what you need to do to let the lens thicken up for near vision. That's called accommodation. So the flatter the lens, the better you see further out, but as soon as you get up close, because that lens has to thicken up, okay? And as you get older, that doesn't happen as well, and you need those reading glasses, okay? But that's called accommodation. You accommodate for near vision. And I've got a slide that mentions that in my head here, so here's one. The iris, everybody knows their pupil will dilate or constrict. The iris is full of smooth muscle as well. Okay? It has a donut ring-shaped system, and it has a radiating system that goes from the edge to the back. So you can imagine what the ring ones will do. When they constrict, it gets smaller, your pupil gets smaller. Okay? When the radiating ones that are just going out, when they pull, it just pulls the iris open. Okay? So now you can guess which one is stimulated by the sympathetic system and which one is stimulated by the parasympathetic system. Okay? The radiating ones that dilate the eye, that's sympathetic. The ones that constrict the eye is parasympathetic. Okay? Okay, so they're connected, like I say, the ligaments here to the ciliary body. We just call it ciliary body. There is you can't really see it on this picture very well, but there's sort of a feathery membrane that runs behind the lens all around the eye, right about to here, and that's called the ora serrata. You'll see that on the beef eye if you haven't already. Okay. Now, we get 3 layers of the eyeball. Okay. The first layer is the retina on the inside. The second layer is a dark layer that has a lot of vasculature and blood vessels in it as well. A lot of melanin. Okay, that's called the choroid here, over here on this side. And then the outside, the tough part of the eyeball, is the sclera. Okay, that's the white part of the eye as well. Okay, that's the sclera that you see on the outside. And so those are the 3 layers. The sclera is more or less continuous with the dura mater. Okay, this is underneath the dura here. Remember I showed you how the cerebrospinal fluid can come up here and put pressure on the back of the optic disc and cause this to blur out. Okay, that causes that papilledema and increased cerebrospinal fluid pressure. So the fovea centralis, okay, that should be on your list. The optic disc, that's the part where the nerve comes into the retina. The optic disc is a circular area right there. Okay, it doesn't have it listed here. So I did this for you. Okay. Yeah.
What were the 3 layers? The
Retina,
choroid, the sclera?
choroid,
The
choroid,
retina,
and the sclera.
the middle is choroid, and the outside is sclera. Okay.
Okay.
And don't confuse the 3 layers of the retina that we're going to talk about here.
That's layers of the
This is
eye.
what you see in the back of the eye when you're looking with the ophthalmoscope. Okay. This is actually a very good ophthalmoscope. The ones, those handheld ones that I'm going to show you how to use. Normally what you're seeing is an area about this size right here. And so you have to look around if you want to see things. Okay?
Wow.
But this is a professional ophthalmologist machine that takes pictures like this. Okay? But here's the fovea. That's where your best vision is again. That's where the images is focused, on the fovea. The macula is a little area, it's a little bigger, okay? And that's also it has a little different tinge. You can see the coloration is a little bit different. Okay. When you get macular degeneration, you've heard of that probably.
Yeah.
Okay. That's what you're doing. You're losing your center of vision. Okay. So people who get that, actually, they've got a big gray spot right in the center of their vision. They can see peripherally, but they can't see what they're looking at. Okay. So, the optic disc, again, this is where the nerve comes in. It has blood vessels with it, and they track out. These are arteries and veins. This is where there are no rods or cones, so you have no vision here. Okay? You have a blind spot there. Did we already do that?
Yes.
Okay. Now you're going to find the blind spot. Okay. So you can see it's off to the side of your center vision. It's about 6-8 inches over here. Okay. These are arteries. Usually the shiny ones are arteries. The veins are a little darker. You can actually see cholesterol plaques in here if the patient has high cholesterol. You can diagnose high cholesterol just by looking in the eye sometimes. If they have high blood pressure, they don't Here's the layers of the retina, okay? This is that dark choroid, the middle layer, the sclera is down here, it's not on the picture, okay? This just happens to be a little pigment area right by the choroid, okay? That's not what I consider part of the layer of the retina. But these darker areas keep light, it's coming down. Our eyes are developed backwards. So, because these are the photoreceptors right here. This is where the rods and cones are. So the light is coming from here, though. It has to go through all the axons, through this layer called the ganglion cell layer, okay? And then through the bipolar neurons and their nuclei, okay? And then through the nuclei of the photoreceptors to get out here. This is where the chemical is that actually is sensitive to light, okay? So our eyes are built upside down. Octopus and squid and things like that, they're built the right way. They get their photoreceptors on the right side. Okay?
As it hits the back of the eye, they get it, but ours has to keep going.
Right.
Dr. Ernst, does that provide more protection for the eye?
What?
Having the layers, the way they're designed like that?
Not particularly. I mean, octopus see fine without any extra protection, you know. It's just the way the eyes develop. The way they fold in on themselves, they're sort of backwards. Okay. And I can remember the eyes are part of your brain. They develop from the diencephalon on your brain, so they're not like a lot of other structures. Okay. And these are so what's going to happen? The light's going to come through. If it hits the photoreceptor down here on a rod or a cone, this cell here has axons. It's going to signal these bipolar neurons. Okay, these are interconnected and then they're hooked up with ganglion cells here. Okay? These are very short bipolar neurons here. Okay? These ganglion cells now have their axons. This is going to go sliding back here to the optic nerve and then head out of the eye. So this is what produces the optic nerve, these cells. Okay? It's their axons. Okay? So it's the ganglion cell layer, the bipolar layer, and then the photoreceptor layer. Okay? And down here, again, is the choroid. You can see it's got a lot of melanin in it, and this pigment layer here is dark as well. Supposedly that helps the photons. Once they get through, they don't reflect. If they don't get absorbed, they don't reflect off of something and go over here and fire off one of these things. So you would have more blurred vision if that was going on. Okay? But you get a nice clear absorption of the light that way. Some animals who live by night, though, they do have a reflective membrane there, and that increases their chances of actually getting that photon to fire off, and so they see better at night that way. Okay. Here's just another picture of the same thing. Here's the sclera, the outside of the eye. Here's the choroid. You can see blood vessels in there as well as the pigment. Here's your photoreceptors, the rods and cones. These are the nuclei of those cells. Okay. Here's the bipolar layer. Here's the ganglion cell layer. Okay. And then all this stuff out here is axons from these things heading off to become an optic nerve. Okay. So just be able to name those three layers for me. Okay. And then be able to name the three layers of the retina as well. Retina, choroid, and sclera. Okay. All right, phobia. Nothing in nature looks like this. This is the back of your eye where the light is focused most directly for the best images. Okay. You can see the bipolar cells and the ganglion cells have gotten out of the way. Okay. That's why the fovea is a special spot on the back of your eye where you get your best vision. Okay. Now the light can come through and it doesn't have to go through all that stuff. Okay. So, but here's the photoreceptors again. These are all mostly cones. Your best center vision is mostly color vision. Okay? And as soon as you get away from the fovea, you start losing your appreciation of color. Okay? And by the time, I know you're in my periphery, you got a bright blue blouse on there, but in my periphery, I can't tell what color that is. Okay? But I can see you. So that's the fovea.
If people have colorblind, is there a thicker layer?
Colorblind, they're missing a different type of cone. I'll show you. I'll explain that in a second. Here's the optic nerve. Here's the three layers of the retina again. All these axons are diving down here like a waterfall. So anytime you see the waterfall, you know that's the optic nerve. All right. So you might see some of these microscopic slides on your tell. So I want you to be able to identify, especially the fovea and the optic nerve. Okay. Okay. This is the ciliary body with the smooth muscle in it, the ligaments that attach to the lens. The lens would be up here. Okay. Here's the canal or phlegm. Okay. This is the anterior chamber with the aqueous humor. And back here, it's called vitreous humor, the gel. What color eye? Could this be?
Brown.
Blue, no blue, it has never.
It's not going to be black or brown. It's going to be bluish, greenish maybe. You know.
Oh, because
Is that
it's
because of
only
that
one
top
layer.
layer, the top?
If this was a dark eye, this melanin would be over here as well.
Oh, okay.
The light's coming this way.
Okay.
The back layer doesn't count.
Wasn't saying that right.
So what's out here is what
That's
counts.
the top, okay, back layer.
Cornea made of collagen. Don't worry about these terms right here. I just wanted to show you. And this is kind of dried out, so it doesn't look really smooth. These fibers are packed in really nice and tight, but they're moist, okay? And they have the same refractive index as that water. Just like when you put fishing line in water, it disappears, okay? That's what happens when collagen fibers get packed in just right, and you moisten them with body fluid, and that they disappear. They become transparent. That's why you can see through the cornea. And the lens is very similar to crystal. This is a slit lamp. This is what you use to look at the cornea. That's the light going through the cornea. It's nice and clear there. It's normal. You don't want to see any little grainy looking sand type particles or crystals in there, or scars, things like that. And you want to see the iris is pretty flat as well. Sometimes the iris can get irregularities in it from different types of problems. So that's just what a slit lamp looks like when you look through it. This is the lens. You can see it sort of has tree ring pattern. Okay. It's what kind of feeling do you think that is?
Cuboidal.
Great. Cuboidal, right. Okay. And these are fibroblasts in here that are making something called crystallins, very similar to collagen, and they pack in tightly as well. When they start to deteriorate and those crystalline proteins are affected by light, strong light, so sunlight can damage them, chemicals can damage them, sugar, carbohydrates can get in there and cause them to split up so they don't transmit the light like they should. That's when you get cataracts. Okay? It's the lens going bad and becoming non-transparent. Okay? Rods and cones. They really do sort of look like rods and little cones. Okay? These are where you get your color vision. Okay? Most of these are in the fovea and the macula. Okay? You've got millions of them. This is the next slide. You've got millions of these, and there's just a few million of these. Okay? But your rods are more sensitive to light. That's why you're using them when you're in the dark. This is what you're using. Your cones aren't firing, so that's why you don't see color in the dark. Opsin is the name of the protein that's in the membrane here. And there are many stacked membranes inside this rod here. The opsin is the name of the transmembrane protein that holds the photoreceptors. Okay? And I'll show you how that works in a second. 120 million rods, 6 million cones. You don't have to remember the numbers, just remember there's a lot more rods than cones. Okay? And depending on what does it say, 100 times more sensitive at night than those of humans. Tremendous number of rods. So that's to have good night vision. You want to have sensitive rods, and you want to have a lot of them. Okay? And what is it, 100 times more than this owl has. But we certainly don't have the best eyes for color or night vision. We have 3 different types of cones that come from mutations of the same gene. Duplication of the gene, then it gets mutated, and then it absorbs at a different frequency. Now you've got 2 frequency light vision. Okay, if that happens again, now you have tricolor vision like we do. Okay, it didn't happen in dogs and a lot of other animals. They've only got the 2 color vision. So that's why you can wear an orange vest and they can't see it. Okay, like a deer. Okay, but we have tricolor vision. We can pass this one. It's just, again, ganglion cells, bipolar cells, photoreceptors. Okay. This is what the pattern looks like. Your rods fire at about this frequency right here. Okay. And then your blue fires lower than that, when something fires, and say the frequency of light is hitting the yellow here and the rod and the red here, or maybe even a little bit of the blue, okay? The same frequency, what your brain is doing is adding up the firing, the amount of firing that's coming from these different types of tones, and it interprets that as a color, okay? So, which is why you can overdo it by staring at a color so long, and then look at a white wall and you'll see the opposite of the color, because you've knocked out the frequency that you were seeing, and your brain is interpreting it as a different color. Okay? Maybe you've also seen this. If we have time, I'll play with a couple of them. Some things can see in the infrared higher up here. Some things can see in the ultraviolet, in the blue down here. Whales and dolphins have the same kind of cones we do, but they have additional mutations that shift the frequency into the ultraviolet so they can see underwater better. Okay? Lots of